Hello students, myself Muhammad Adil Sheikh, Assistant Professor of Chemical Engineering Department from LJ Institute of Engineering and Technology. Today we will talk about process equipment designing, in which we are going to learn about types of packing, liquid distributor, liquid redistributor, packing support, and then we will talk about falling film absorber and its process designing steps. So let us continue. We will start with the types of packing. So the packings are divided into two groups, random packing and regular packings. So the regular packings that are used are grids, structured packing, stacked rings, rashing rings, etc. The grids are used for high gas velocity, as they offer very low pressure drop, and they are used in a cooling towers. Structured packings are used in a chemical process industries very frequently, because they are made from corrugated sheets with some perforations or wire meshes. They provide higher surface area with a higher void fractions. They are preferred for difficult distillation operations, for high vacuum distillation, for high efficiency in absorption with a lower allowable pressure drop, and also increasing capacity of existing tower distillation column. Here are the figure for the same, the regular packings. Now the random packings. So the random packings are most commonly used random packings are pall rings, ball saddles, interlock saddles, rashing rings, etc. Now the pall rings are preferred and commonly used random packing, because they provide a very high cost per unit volume. So they also require minimum tower diameter and minimum height for given absorption duty or distillation duty as compared to the other random packings. If we are using corrosive systems, then ceramic ball saddles are cheaper than the metallic pall rings, so we can use ceramic ball saddles for the same. For a very high temperature and corrosive services, glass packed with a glass rashing rings are preferred against a packed column with a special alloy. So the figure for the same, that the random packings. Now to avoid the deterioration of a random packings while filling up in the packed columns, the packed tower is first filled with the water, and then the random packings are dumped at the random places within the tower. Now the liquid distributor. So the liquid is filled in a packed column. It is must for them to distribute evenly among all the packing, so that they provide better gas liquid efficiency. Now for a small tower diameter of a packed column, tower diameter less than 0.3 meter, single point distributor like one spray nozzle is enough. But for the large tower diameter of a packed column, multi-point distributors like perforated pipe distributor, through type distributor, orifice distributor, etc. are used. Now we will see the first is a perforated pipe distributors. So they are preferred for the column diameter ranging from 0.3 to 1 meter, and they are used with a clean liquid and offers minimum restrictions to the gas flow. As you can see, the perforated pipe distributor, they consist of several pipes with the spray nozzle at uniform distance, and so they provide even distribution of a liquid all over the packed bed. Now the second one is a through type distributor. So they are preferred for the column diameter greater than or equal to 1.2 meter. It can be used with a liquid having solids in a suspension. It consists of a series of throughs containing side notches, and it provides good liquid distribution with a large free area for the gas flow. So as you can see, it consists of side notches through which the liquid will be distributed evenly along the entire bed of packings. Now the third one is a orifice type distributor, and it is also preferred for the large diameter packed column. This type of distributor consists of a flat perforated tray equipped with a number of risers or short stand pipes, through which the gas will rise upward. So the gas will rise upward through the risers or stand pipes, while the liquid will be maintained certain level over the perforated tray, and will flow down through the perforations. So there will be some holes over the tray, so that they are small enough to ensure that there will be a certain level of a liquid over the plate is maintained at a lowest liquid rate, but large enough to prevent distribution overflowing at a higher rate. So as you can see, there are risers through which the gas will pass, and there are small perforated holes through which the liquid will be passed downward. Now the last one is a weir type distributor. So in the weir type distributor, gas and liquid both will be flowing through the same stand pipes. It consists of a nosed weirs in the upper portion, and the certain level of liquid will be maintained over the tray, and the liquid will flow over the same nosed weir and will flow down, and the gas will rise upward through the same pipe. You can see here that there are some notches, and to maintain the liquid level, and the gas and liquid both will pass through the same pipe. Now a liquid redistributor. So after traveling certain level within the packing bed, the liquid will migrate toward the column wall and will flow in the vicinity of that column wall, while the gas will rise upward through the certain portion, and so there won't be gas liquid the better gas liquid contact. This phenomena is called as channeling. So the liquid redistributor will do that it will collect the liquid that has migrated towards the wall and will redistribute it evenly over the next bed of the packing, so that the better gas liquid contacting efficiency will be obtained. Now there are different types of redistributor that are used. The first one is a wiper redistributor, the second is a bell cap redistributor. Now the packing support. So the function of a packing support is to carry the load of a wet packing bed without providing excessive restriction to the gas and liquid flow. And also it will act as a distributor for both the streams. Now if we design packing support poorly, then it provides higher pressure drop and can cause to the premature local flooding. And the different types of packing supports used in a pack tower are countercurrent type and separate flow or a gas injection type. Now we will talk about falling film absorber. So the falling film absorber is generally a shallow tube heat exchanger in which the absorption of a gas in a liquid is carried out inside the tube, while the cooling medium like cooling water will be circulated over the shell side. They are generally used for a very high exothermic absorption. The advantages for the falling film absorber is that it provides better quality of a product solution, and absorption is more efficient in a falling film absorber for the given absorption duty, and it requires very less space as compared to the other type of absorbers. And the other advantages for the falling film absorber is lower temperature, lower pressure drop, and higher turn ratio. There are certain disadvantages of the falling film absorber. So let us see that. The first one is that it is more difficult to control and is very sensitive to the liquid and gas distribution problem, and it has a greater tendency to absorb undesirable water soluble low boiling impurities. So now the process design of a falling film absorber. So we will consider the example of absorption of HCl in a water. So first of all, we will fix the inlet and outlet concentration of HCl, and also we will fix the concentration of HCl in a exit gas stream. The outlet temperature and concentration of gas and liquid both will be fixed. Now we will determine the overall rate of absorption based on the same, and also determine the total heat duty. The rate of absorption and the rate of heat transfer required will are changing from point to point in the heat exchanger. So based on a heat balance, we will find the flow rate of a cooling medium, and in the end the heat transfer area of a falling film absorber must be determined. So the equation for the same is A is equals to Nt into pi d0L, which is equals to Q upon U delta Tm. Now to facilitate two-phase flow, the DO, that is pipe outside diameter, can be selected as 25.4 mm. Nt, which is number of tubes, that can be decided based on the following criteria. The first one is that if for a co-current contact velocity of a feed gas mixture at inlet should be less than or equal to 18.3 meter per second, and so to get a higher rate of mass transfer at a gaseous velocity in the tube should be around 15 meter per second. Now for efficient operation of a falling film absorber, certain minimum liquid flow rate is required to maintain continuous film over the tube wall. Now once the velocity of the gas is fixed, the flow rate of a liquid per unit periphery of a tube is fixed by the material balance, and reverse is also possible. So the tube length can be easily determined based on the above equation, that is L, the length of a tube. Now the rate of absorption, rate of heat transfer, overall heat transfer coefficient and temperature difference across the heat transfer wall are changing from point to point in a falling film absorber. So for the precise calculation, we can cut down heat exchanger into different zones, and for each zone the length can be determined. So for each zone, the rate of absorption, heat duty and temperature difference can be calculated easily. Now the rate of absorption of a gas is given by this equation, that is Na is equals to Kg into M into rho Ag minus rho Pag minus Pal, and the value of rate of absorption will be Kg per meter second. So Kg is overall mass transfer coefficient based on the arithmetic mean partial pressure difference. M is a molar mass of gas absorbed in Kg per kilomole. Pag is partial pressure of a solute gas in a gas mixture. PAL is the equilibrium partial pressure of a solute A at a gas liquid interface. Now the mass transfer coefficient for the for HCl absorption can be determined by the following equation, that Kg is equals to 1.654 into 10 to the power minus 5 divided by MAV raised to 1.75 multiplied by BIGI upon mu. Now what are the terms? That Di is the inside diameter of the tube in meter, Gi is the mass velocity of a gas mixture at the inlet in kg per meter square second, mu is the viscosity of a gas mixture in kg per meter second, and Mag is a average molar mass of a gas mixture at a inlet. Okay, then the last is the tube side heat transfer coefficient, that H is equals to 9136 multiplied by tau raised to 1 by 3. Now what is tau? Tau is a liquid flow rate per unit periphery, that is kg per meter second, and the tau should be between range of 0.25 to 6.2. So here the process design of falling film absorber ends. I hope you all have understood this. Thank you.